February 23, 1945, Iwo Jima, Volcano Islands. The 3rd Marine Division struggles across black volcanic sand as Lieutenant General Tadamaki Kuribayashi's 21,000 defenders mass behind reinforced concrete fortifications. In the assault platoons, Marine Demolition Sergeant Corporal Herschel Woodrow Williams checks his 70-pound M22 portable flame projector one final time. Today, Louis Fieser's revolutionary napalm formula will face its ultimate test against the most fanatically defended Japanese strongpoint in Pacific War history. The story begins not in the volcanic ash of Iwo Jima, but in the basement laboratory of Harvard University's Converse Chemistry Laboratory on Oxford Street in Cambridge, Massachusetts, where Professor Louis Frederick Fieser worked under the strictest wartime security. Born April 7, 1899 in Columbus, Ohio, Fieser began as an organic chemistry researcher, studying quinone oxidation potentials under James Bryant Conant's direction. When America entered World War II, this brilliant academic would create something that would revolutionize infantry warfare permanently. Working under the National Defense Research Committee's highly classified Division 19 program, Fieser confronted the fundamental problem plaguing incendiary weapons since World War I. Observing how gasoline-based flame fuels dissipated ineffectively after leaving weapon nozzles, consuming themselves in spectacular but brief explosions, rather than maintaining coherent, sustained burns, Fieser designed a revolutionary thickening agent using aluminum naphthenate and aluminum palmitate compounds. His breakthrough concept was so transformative that when perfected on February 14, 1942, Valentine's Day, it would alter battlefield dynamics across every theater of operations. During the late 1930s and early 1940s, the United States military faced critical gaps in infantry support capabilities. Conventional flame weapons, like the problematic Monet, could barely project burning fuel 20 yards effectively, suffering from unreliable ignition systems, inconsistent fuel mixtures, and limited operational duration. Artillery could engage targets thousands of yards distant, while individual rifles and machine guns dominated shorter ranges. But between these weapon systems lay a deadly tactical void, where enemy troops could establish seemingly impregnable strongholds in reinforced bunkers, cave complexes, and fortified structures that conventional weapons simply couldn't neutralize effectively. The American Chemical Warfare Service, recognizing these limitations through early Pacific combat experience, initiated comprehensive development programs to create superior incendiary weapon systems. Unlike European theaters, where mobile warfare predominated, Pacific Island fighting demanded weapons capable of eliminating heavily fortified Japanese defensive installations that had been constructed specifically to withstand conventional artillery and aerial bombardment. In 1941, American military engineers examined various flame projector designs from multiple sources, but quickly determined that indigenous development would be necessary to meet specific tactical requirements. The Chemical Warfare Service established development contracts with several American manufacturers, revising technical specifications to incorporate lessons learned from early combat operations, while adapting designs for American manufacturing capabilities and logistical systems. When these comprehensive modifications were completed, the weapons were designated as the Monet Portable Flame Projector, followed by the significantly improved Monet-own model, incorporating napalm fuel technology. The Chemical Warfare Service, originally established during World War I to develop chemical weapons, became the engineering center of America's flame weapon revolution, but this new program represented something entirely different from previous chemical warfare initiatives. The incendiary weapon program wasn't designed to create area denial weapons or mass casualty systems like poison gas. Instead, these weapons were precision instruments, designed to provide devastating close-range firepower directly to Marine rifle companies, enabling them to eliminate specific fortified installations that were stopping entire battalion advances. In March 1942, initial production contracts for flame weapon systems were issued to multiple American manufacturing companies, including specialized firms with experience in pressure vessel construction and fuel system engineering. As Pacific War requirements expanded exponentially, production demand grew beyond all initial projections. The Firestone Tire and Rubber Company joined the manufacturing consortium, contributing expertise in rubber fuel lines and pressure-resistant components, while other contractors focused on metallurgy, ignition systems, and precision manufacturing. By war's end, American industrial capacity would produce over 25,000 individual flame projector systems, plus hundreds of thousands of fuel canisters, replacement components, training devices, and specialized accessories. This massive production effort represented more than just weapon manufacturing, themasayo day to industry. It demonstrated American industry's ability to rapidly transition from peacetime consumer goods to sophisticated military equipment while maintaining quality control and delivery schedules under wartime pressure. The weapon system that emerged from American factories was deceptively simple in appearance, yet represented revolutionary engineering achievements. The Moneon weighed 65 pounds when fully loaded with fuel and compressed nitrogen propellant, configured as a backpack system that distributed weight across the operator's shoulders and back. The entire system could be disassembled into manageable components for transport, maintenance, and field repair by trained marine technicians. The truly revolutionary feature was FISA's napalm thickening compound, sticky, jellied fuel mixture that maintained coherent flame streams over extended ranges, instead of dissipating like conventional gasoline-based systems. This technological breakthrough represented the difference between ineffective weapons that endangered their operators and devastating systems that could eliminate any fortified installation. The napalm-equipped Moneon could project sustained flame streams up to 40 yards with devastating accuracy and precision. Unlike earlier gasoline-based systems that created brief, explosive bursts, consuming their fuel loads within seconds, napalm burned intensely for extended periods while adhering tenaciously to any surface it contacted. The fuel mixture burned at temperatures exceeding 2,000 degrees Fahrenheit, hot enough to melt steel, crack concrete, and penetrate the most sophisticated defensive construction. A trained marine operator could maintain sustained fire for 6 to 8 seconds per fuel load, but tactical doctrine emphasized multiple precise bursts to maximize effectiveness while conserving fuel for extended engagements. The adhesive properties of napalm meant that even brief contact with defensive installations created continuing fires that made those positions untenable for defending troops. The napalm formula created flames that could flow like liquid around defensive obstacles, through firing ports and ventilation systems, and into supposedly protected areas where defenders assumed they were safe from external attack. This capability made traditional defensive tactics obsolete. Installations that had been considered impregnable became death traps when attacked with properly employed flame weapons. However, the Moneon still suffered from ignition system reliability problems inherited from the original Monet design. The hydrogen-powered ignition system frequently failed under combat conditions, forcing operators to improvise ignition methods using burning paper, cigarette lighters, or other available materials. This fundamental weakness would drive the development of the superior M22 system that would prove decisive in later Pacific campaigns. By 1943, the Chemical Warfare Service had developed comprehensive understanding of what infantry troops needed from their portable incendiary weapons based on extensive after-action reports and feedback from Pacific operations. This accumulated combat experience led directly to the development of the significantly improved M22 system with its revolutionary rotary cartridge ignition mechanism. The M22 addressed every major deficiency identified in earlier designs while incorporating advanced features that made it the most effective infantry flame weapon ever developed. The new ignition system eliminated the hydrogen cylinder and unreliable electrical components, replacing them with a robust rotary cartridge system containing 5 individual pyrotechnic ignition charges that provided completely reliable ignition under any combat conditions. The improved weapon weighed 70 pounds when fully loaded with 4 gallons of napalm-thickened fuel distributed across 2 main fuel tanks and 1 smaller nitrogen propellant tank, configured as a comfortable backpack system. The fuel capacity provided approximately 8 seconds of total firing time, which could be divided into multiple precise bursts for maximum tactical effectiveness. The M22's operational range extended up to 40 meters under optimal conditions, with an effective engagement range of 20 meters against fortified targets. The weapon's high-angle trajectory allowed operators to attack targets in defilade positions that conventional weapons couldn't reach, while the napalm's adhesive properties ensured that flame penetrated into defensive positions and continued burning regardless of defender attempts at suppression. Marine rifle companies developed sophisticated organizational structures around incendiary weapon operations throughout the Pacific War. Initially, three-man teams operated within weapons platoons under platoon sergeant supervision. The team consisted of a primary operator carrying the complete weapon system, an assistant gunner responsible for fuel supplies, spare equipment, and immediate security, and an ammunition bearer who managed additional fuel canisters, replacement components, and protective equipment for extended operations. By 1944, Marine Corps tactical doctrine had evolved to place these teams under direct company commander control, reflecting hard-learned lessons from Pacific Island combat. Company commanders needed immediate, responsive flame support that could adapt instantly to rapidly changing tactical situations without requiring coordination through higher headquarters or complex approval processes. This organizational evolution meant Marine companies could position incendiary weapon teams to solve specific tactical problems that heavier weapons couldn't address effectively. The weapon's relative portability allowed rapid deployment to support changing battle conditions, while its devastating effectiveness against fortified installations made it the preferred solution for neutralizing defensive strongpoints that were stopping entire infantry advances. The tactical flexibility provided by organic flame support revolutionized Marine small unit operations. Company commanders could eliminate individual bunkers, clear cave complexes, neutralize machine gun nests, and overcome defensive installations that might otherwise require prolonged artillery bombardment or costly frontal infantry assaults with inevitable heavy casualties. Marine doctrine emphasized combined arms coordination, integrating flame attacks with supporting fire from Browning automatic rifles, individual Marine riflemen, and when available, tank support or artillery preparation. The psychological impact of flame weapons was as significant as their physical destructiveness. Japanese defenders often abandoned seemingly impregnable installations when they observed these teams approaching, preferring to fight in the open rather than be trapped in fortifications that had become furnaces. The development of tank-mounted flame systems provided additional capabilities for attacking larger installations that were beyond the reach of portable weapons. The M3 Aoun Satan tanks, converted from M3 Stuart light tanks, carried 400 gallons of napalm-thickened fuel and could project flames up to 150 yards. These armored systems provided protection for operators while delivering massive volumes of incendiary material against major defensive complexes. During the Battle of Saipan in June and July 1944, American forces first employed comprehensive flame weapon tactics, integrating portable systems with tank-mounted projectors and coordinated infantry support. The results demonstrated the decisive advantage provided by systematic application of incendiary weapons against Japanese defensive installations that had been designed to withstand conventional attacks. Japanese defenders on Saipan had constructed elaborate cave systems throughout the island's mountainous interior, utilizing natural formations enhanced with concrete reinforcement, steel doors, and sophisticated ventilation systems. These installations were virtually immune to artillery bombardment and aerial attack, but proved vulnerable to flame weapons that could penetrate cave entrances and fill interior spaces with superheated napalm. The success of flame weapon operations on Saipan validated tactical concepts that would be refined and perfected in subsequent campaigns. American commanders learned to coordinate multiple weapon systems in systematic attacks that eliminated entire defensive complexes rather than individual positions, while Japanese defenders discovered that their most sophisticated fortifications provided no protection against properly employed incendiary attacks. At Guam in July and August 1944, Marine units equipped with the new M22 systems demonstrated the weapon's superior capabilities during prolonged cave-clearing operations. The improved ignition system eliminated the reliability problems that had plagued earlier models, while the increased fuel capacity allowed sustained operations against multiple targets without requiring frequent resupply. One particularly significant engagement occurred when Corporal Herschel Williams, serving with the 21st Marines, led a coordinated attack against a complex of interconnected Japanese cave positions that had stopped an entire battalion advance for 2 days. Williams and his supporting team systematically eliminated 12 separate cave entrances using coordinated flame attacks supported by covering fire from BAR gunners and riflemen. The tactical success at Guam demonstrated how individual Marines equipped with superior technology and proper training could achieve results that might otherwise require company-sized operations with corresponding casualties. Williams's performance during the Guam campaign established him as one of the most effective flame weapon operators in the Pacific theater, experience that would prove crucial during the subsequent Iwo Jima operation. At Iwo Jima, as Kuribayashi's troops prepared their elaborate defense-in-depth strategy, American Marines had been refining incendiary weapon tactics through successive campaigns across the Central and Western Pacific. The volcanic island represented the ultimate test of both American amphibious capabilities and flame weapon effectiveness against the most sophisticated Japanese defensive system ever constructed. Kuribayashi's defensive plan was revolutionary by Japanese standards, 1920. Instead of attempting to repel the invasion at the beaches, Japanese troops would allow American forces to land, then subject them to devastating crossfire from concealed installations throughout the island's interior. This strategy was specifically designed to maximize American casualties while prolonging the battle for as long as possible. The defensive complex included over 18 miles of interconnected underground tunnels, hundreds of reinforced concrete bunkers and pillboxes, carefully positioned artillery emplacements with overlapping fields of fire, and thousands of individual fighting positions carved into the volcanic rock. Every defensive installation was constructed to survive heavy naval bombardment and aerial attack, while maintaining clear fields of fire against advancing American infantry. Japanese engineers had studied American tactics from previous campaigns, incorporating countermeasures specifically designed to neutralize incendiary weapons and other specialized equipment. Ventilation systems were constructed to prevent gas or flame accumulation. Multiple escape routes allowed defenders to evacuate threatened installations, and interlocking defensive arrangements ensured that elimination of individual positions wouldn't compromise overall defensive integrity. American attacking units included the 3rd, 4th, and 5th Marine Divisions, TPO, over 70,000 assault troops supported by the most massive naval and air bombardment in Pacific War history. These formations had been developing and refining flame weapon employment through campaigns at Guadalcanal, Tarawa, Saipan, Guam, and other Pacific battlefields, accumulating tactical expertise that would prove crucial on Iwo Jima. At 0900 hours on February 19, 1945, the first Marine assault waves struck Iwo Jima's southeastern beaches. 30,000 Marines charged across black volcanic sand under surprisingly light initial resistance, but this apparent Japanese weakness was actually part of Kuribayashi's strategic deception. Japanese troops allowed the landings to proceed, then unleashed devastating defensive fire from concealed installations throughout the island. Within hours, American casualties mounted exponentially as Marines encountered defensive installations unlike anything faced in previous Pacific operations. Reinforced concrete bunkers had been constructed to channel attacking units into predetermined killing zones, while interconnected tunnel systems allowed Japanese defenders to reinforce threatened sectors or escape from installations under direct attack. Traditional American tactical solutions proved inadequate against Kuribayashi's defensive innovations. Artillery bombardment, even with the heaviest naval guns available, couldn't reach defenders in deep underground installations. Tank support was limited by the island's volcanic terrain and extensive anti-tank obstacles. Infantry assaults resulted in prohibitive casualties without achieving decisive tactical results. But Japanese defensive planners had underestimated the effectiveness of American flame weapon tactics when properly coordinated with supporting weapons and employed by expertly trained Marines. The napalm-based systems could reach defensive installations that conventional weapons couldn't touch, while the adhesive properties of the fuel made defensive positions untenable even for the most determined defenders. On February 21st, Corporal Herschel Woodrow Williams landed on Iwo Jima with the 1st Battalion, 21st Marines, 3rd Marine Division. Williams, born October 2, 1923 on a dairy farm in Quiet Dell, West Virginia, had initially been rejected by the Marine Corps for failing to meet height requirements. At 5 feet 6 inches, he was considered too short for military service until personnel needs and modified standards allowed his enlistment in May 1943. Williams had trained as a demolition specialist and flame weapon operator, serving with distinction during the Guam campaign in 1944. His experience with explosive charges and incendiary systems made him invaluable for the specialized combat that characterized Pacific Island warfare, where individual Marines often had to eliminate heavily fortified installations through close combat techniques. 2 days after landing, on February 23rd, The same day American flags were raised on Mount Suribachi. 2023, Williams faced the tactical situation that would earn him the Medal of Honor and demonstrate the ultimate effectiveness of American flame weapon technology against seemingly impossible defensive installations. American tanks attempting to open corridors for infantry advance had encountered a network of reinforced concrete pillboxes, buried anti-tank mines, and carefully prepared obstacles that stopped the armored advance completely. Machine gun fire from the pillboxes was inflicting heavy casualties on any Marines who attempted to advance across the open ground, while the defensive installations themselves appeared impregnable to conventional weapons. Williams volunteered to attempt reducing the defensive installations using his M22 system, despite the obvious dangers involved in approaching heavily defended bunkers with a weapon that required close-range employment. 4 Marine riflemen, Private First Class Warren Bornholtz, Private First Class Charles Fisher, Private First Class Howard Chambers, and Private First Class Glenn Schwartz, Williams, volunteered to provide covering fire for Williams's assault. The attack began with Williams crawling forward across the volcanic sand and rock, while his covering team attempted to suppress Japanese defensive fire with rifle and automatic weapon fire. The approach required Williams to cross several hundred yards of open ground while carrying a 70-pound weapon system and exposed to intense enemy fire from multiple installations. Williams reached the first pillbox and inserted his weapon nozzle through a firing port, filling the interior with superheated napalm that killed all occupants instantly. The success encouraged him to continue the attack against additional installations, but the covering fire team was already taking casualties from concentrated Japanese defensive fire. The battle continued for over 4 hours, with Williams repeatedly returning to Marine lines to obtain refueled systems and additional demolition charges, while the Japanese defenders concentrated increasingly heavy fire on his location. Each successive attack required Williams to approach different pillboxes from various angles while under direct observation and fire from multiple enemy installations. During one particularly dangerous approach, Williams climbed directly on top of a concrete bunker to insert his weapon nozzle through an air vent, eliminating the occupants while completely exposed to enemy fire from surrounding positions. On another occasion, he encountered Japanese infantry attempting to stop his advance with bayonet charges, eliminating them with point-blank flame attacks that consumed the oxygen from their immediate environment. By the end of the 4-hour engagement, Williams had single-handedly eliminated 7 heavily fortified Japanese installations that had been stopping the entire American advance in that sector. The tactical breakthrough allowed Marine infantry to move forward and establish positions that had been impossible to reach under the previous defensive fire. 2 of his covering team, Bornholtz and Fisher, had been killed during the action, while Chambers and Schwartz survived with wounds. Williams's assault demonstrated the ultimate capability of American flame weapon technology when employed by expertly trained personnel under the most extreme combat conditions. The tactical success opened corridors for further Marine advances while eliminating defensive installations that might have required days of fighting and hundreds of additional casualties to reduce through conventional methods. The psychological impact of Williams's attack extended far beyond the immediate tactical results. Japanese defenders throughout the area had witnessed American flame weapons systematically eliminating installations they had considered impregnable, demonstrating that no defensive construction could provide adequate protection against properly employed incendiary attacks. Williams continued fighting on Iwo Jima throughout the remainder of the 5-week campaign, surviving until March 6 when he was wounded by shell fragments and evacuated for medical treatment. Of over 300 American flame weapon operators deployed on Iwo Jima, fewer than 20 survived the complete battle, a casualty rate reflecting both the weapon's tactical importance and the extreme dangers faced by operators who had to approach enemy installations at close range. The extraordinary casualty rate among flame weapon operators resulted from several factors inherent to their tactical employment. The weapons required close-range engagement, typically within 40 meters of enemy installations, exposing operators to concentrated defensive fire. The distinctive appearance of the backpack systems made operators priority targets for enemy marksmen and artillery observers. The fuel-filled tanks, while not explosive when hit by small arms fire, created distinctive pressure releases that revealed operator locations. Despite these dangers, demand for flame weapon systems continued to grow throughout Pacific operations. Marine divisions that had initially deployed with 24 portable systems by 1944 were requesting over 200 units per division, with some regiments maintaining organic flame weapon sections of 81 operators and supporting personnel. The tactical effectiveness of these weapons against Japanese defensive installations was so pronounced that enemy forces began modifying their construction techniques and defensive doctrines specifically to counter American incendiary attacks. Japanese engineering manuals from 1944 and 1945 reveal detailed countermeasures, including improved ventilation systems, flame-resistant materials, water suppression equipment, and modified bunker designs intended to limit flame penetration. Williams returned to the United States in September 1945 and received the Medal of Honor from President Harry S. Truman on October 5, 1945, in a White House ceremony attended by 13 other Medal of Honor recipients. The citation recognized Williams's conspicuous gallantry and intrepidity at the risk of his life above and beyond the call of duty during the Iwo Jima assault. The official citation detailed Williams's 4-hour single-handed assault against Japanese defensive installations, noting his repeated returns to friendly lines for refueled weapons while under continuous enemy fire. The document emphasized that Williams's actions were directly instrumental in neutralizing one of the most fanatically defended Japanese strongpoints encountered by his regiment, and enabled his company to achieve objectives that had been impossible under previous defensive fire. Williams's Medal of Honor represented more than individual heroism, MMO. It validated the tactical concepts and technological innovations that had transformed American infantry capabilities in Pacific warfare. The recognition demonstrated how individual initiative, superior training, and advanced technology could combine to achieve tactical results that conventional approaches couldn't accomplish. Japanese military analysts studied American flame weapon effectiveness with growing alarm throughout the Pacific War. Captured documents from Iwo Jima reveal detailed assessments of incendiary weapon capabilities and desperate attempts to develop effective countermeasures against American tactical innovations. Japanese tactical reports acknowledged that American infantry companies possessed immediate flame support that made traditional defensive strategies ineffective. Previous Japanese defensive doctrine had assumed that heavily fortified installations could withstand American attacks long enough for reinforcements to arrive or counterattacks to be organized, but flame weapon attacks eliminated defensive positions too quickly for such strategies to succeed. A captured Japanese analysis from Iwo Jima stated that American infantry units could eliminate concrete fortifications within minutes using portable fire weapons that penetrate any defensive opening. The report noted that Japanese defenders were psychologically unprepared for weapons that make retreat from defensive positions impossible due to adherent burning fuel. Japanese engineering efforts attempted to counter American flame weapon effectiveness through modified bunker construction, incorporating improved ventilation systems, multiple compartments to limit flame penetration, and alternative escape routes to allow defenders to evacuate threatened installations. Some defensive positions included water supplies for fire suppression and specialized equipment for treating burn casualties. Experimental Japanese countermeasures included flame-resistant coatings for interior bunker surfaces, carbon dioxide fire suppression systems, and modified ventilation designs intended to prevent napalm accumulation in defensive spaces. Some installations incorporated multiple chambers connected by narrow passages designed to limit flame propagation between defensive sections. But Japanese countermeasures proved fundamentally inadequate against American tactical innovations and technological superiority. Marine flame weapon teams learned to coordinate attacks from multiple directions, ensuring comprehensive coverage of target areas while preventing Japanese defenders from utilizing escape routes or compartmentalized protection systems. The fundamental problem facing Japanese defensive planners was that napalm could penetrate any opening large enough for defensive weapons or personnel, while the adhesive properties meant that even brief flame contact made defensive installations uninhabitable. Ventilation systems designed to prevent flame accumulation actually facilitated napalm distribution throughout defensive complexes, while escape routes became conduits for flame penetration into supposedly protected areas. Japanese tactical doctrine emphasized spiritual preparation and acceptance of death in defensive installations, but these philosophical approaches proved irrelevant against weapons that made defensive positions physically uninhabitable, regardless of defender determination or courage. The psychological impact of facing imminent incineration forced even the most dedicated Japanese defenders to abandon installations or attempt desperate counterattacks that exposed them to American supporting fire. Captured Japanese documents reveal growing desperation among defensive commanders facing systematic American flame weapon attacks. One report from Okinawa described American tactics as impossible to counter with conventional defensive measures, and noted that fire weapons eliminate entire defensive sections regardless of construction quality or garrison determination. As the Pacific War progressed through 1944 and 1945, American production of flame weapon systems and napalm fuel reached unprecedented levels. Monthly production exceeded previous annual totals as military requirements expanded across all Pacific theater operations. Firestone Tire and Rubber Company operated continuous manufacturing shifts, while other contractors expanded production facilities and hired additional skilled workers. The Reed Machinery Company in York, Pennsylvania, became the primary manufacturer of M22 systems, producing over 8,000 units during 1944 and 1945. Kennedy Vanson Engineering Company in Danville, Pennsylvania, contributed specialized components including pressure regulators, valve assemblies, and ignition cartridge systems that were crucial to weapon reliability. The Chemical Warfare Service continued refining manufacturing processes, quality control procedures, and logistics systems throughout the war. Production facilities employed thousands of specialized workers at peak capacity, producing not just weapons but complete systems, including fuel mixing equipment, protective gear, training devices, maintenance tools, and specialized accessories for various tactical applications. Quality control procedures included hydrostatic testing of all pressure vessels at 600 pounds per square inch, 2 SS, more than double operational pressure, to ensure safety margins under extreme combat conditions. Each weapon underwent complete functional testing, including ignition system verification, fuel flow calibration, and range testing before shipment to combat units. American production represented more than just weapon manufacturing, embodied industrial democracy's capacity to rapidly mobilize resources, apply technological innovation, and mass-produce sophisticated military equipment while maintaining quality standards under extreme time pressure. The scale and efficiency of American production demonstrated industrial capabilities that no other nation could match during World War II. The Moneoni and later M22 systems represented the translation of university-level scientific research into practical military hardware that could be manufactured in quantities sufficient to equip every Marine rifle company in the Pacific Theater. FISA's original Harvard research had provided the theoretical foundation, but American engineers and manufacturers transformed laboratory concepts into reliable weapons that functioned effectively under the most demanding combat conditions. This production achievement had strategic implications extending far beyond individual battles or tactical situations. Japanese units found themselves facing American troops equipped with superior weapons in overwhelming quantities, while Japanese industry struggled to produce adequate quantities of conventional weapons and ammunition for basic defensive requirements. The tactical flexibility provided by widespread flame weapon availability was revolutionary in infantry warfare. American company commanders could eliminate fortified installations without requesting support from higher headquarters, coordinate multiple incendiary attacks simultaneously to support complex tactical maneuvers, and adapt to changing battlefield conditions with immediate, decisive firepower that could overcome any defensive position. Japanese commanders operating under traditional military doctrines couldn't match American responsiveness and tactical flexibility. By the time Japanese units could coordinate defensive measures or organize counterattacks, American forces had already eliminated key defensive installations and achieved tactical objectives through systematic flame weapon employment supported by coordinated infantry operations. This technological and tactical superiority became increasingly apparent as American units advanced closer to Japan itself during 1945 operations. Japanese defensive preparations became more sophisticated and determined, but American flame weapon capabilities continued to prove decisive against even the most elaborate fortifications and prepared positions. On Okinawa, April through June 1945, Japanese troops had constructed elaborate defensive systems throughout the island's interior, utilizing natural cave complexes, reinforced positions, and carefully prepared obstacles to maximize American casualties while prolonging the battle. Lieutenant General Mitsuru Ushijima commanded over 100,000 defenders, armed with extensive artillery, numerous machine guns, and carefully coordinated defensive plans. American units included multiple Marine and Army divisions equipped with hundreds of flame weapon systems and massive quantities of napalm fuel. The battle demonstrated incendiary weapon effectiveness against cave complexes and reverse-slope defensive installations that conventional weapons couldn't reach effectively. The weapon's ability to project napalm into cave entrances, through ventilation systems, and around defensive obstacles proved crucial to American tactical success on Okinawa. While casualties remained heavy, American units suffered over 49,000 casualties while Japanese losses exceeded 77,000. Flame weapons contributed significantly to tactical victories that would have been impossible through conventional methods alone. Throughout the Okinawa campaign, over 200,000 gallons of napalm-thickened fuel were used against Japanese defensive installations in caves, hills, cliffs, and fortified areas. Tank-mounted systems supplemented portable weapons, providing extended range and larger fuel capacity for attacking major defensive complexes. The Satan tanks proved particularly effective against large cave systems that were beyond the reach of portable weapons. These modified M3 Aeon systems could project flame streams up to 150 yards, while providing armored protection for operators. During one notable engagement, a single Satan tank eliminated a complex of 17 interconnected caves that had stopped infantry advances for 3 days. Marine Corps documentation from Okinawa reveals systematic flame weapon employment that eliminated over 1,200 individual Japanese defensive installations during the 82-day campaign. This tactical success validated all previous development efforts and demonstrated that American incendiary weapon capabilities had reached maturity as decisive infantry support systems. The success of flame weapon operations on Okinawa validated all previous tactical development and demonstrated that American capabilities had reached maturity as decisive infantry support weapons. Japanese defensive preparations, regardless of sophistication or determination, couldn't withstand systematic attacks supported by coordinated American tactics. Statistical analysis of Okinawa operations revealed that defensive installations attacked with flame weapons were eliminated within an average of 12 minutes, compared to over 6 hours required for conventional methods. This tactical efficiency translated directly into reduced American casualties and accelerated operational tempo that Japanese defenders couldn't match. As World War II approached its conclusion in August 1945, American military planners were already developing improved systems for future conflicts. The Monoe had proven effective across diverse tactical situations, including jungle warfare, amphibious assaults, urban combat, cave-clearing operations, and conventional infantry fighting, but advancing technology promised even greater capabilities. Development continued through the Korean War and early Vietnam operations, with improved systems providing extended range, larger fuel capacity, and enhanced reliability. The basic principles established by FISA's napalm research and American tactical innovations during World War II remained fundamental to flame weapon employment for decades. However, the strategic context of warfare was changing rapidly with nuclear weapons, guided missiles, and other technological advances that reduced the relative importance of infantry flame weapons. While these systems remained tactically effective, their role in overall military strategy became increasingly specialized and limited. The weapons would eventually be replaced by more advanced systems in the 1970s, including rocket-propelled incendiary weapons, improved demolition devices, and precision-guided munitions that could achieve similar tactical results without requiring close-range employment. But the impact of flame weapons on military tactics and American industrial development had already secured their place in warfare history. Post-war analysis revealed that flame weapons had eliminated over 15,000 individual Japanese defensive installations throughout Pacific operations, from Guadalcanal through Okinawa. This tactical achievement represented more than statistical success, SAC. It demonstrated how scientific innovation could revolutionize warfare when supported by adequate industrial production and comprehensive training programs. FISA's research achievement represented something truly remarkable. A university chemistry professor had created incendiary technology that gave individual infantry companies firepower capabilities previously available only to specialized units, or heavy weapons organizations. American engineers refined and mass-produced this innovation to equip the largest military force in world history, while tactical developers created employment doctrines that maximized weapon effectiveness. The result was a weapon system that helped American infantry dominate Pacific battlefields from Guadalcanal through Okinawa. Japanese units, despite exceptional courage, determination, and sophisticated defensive preparations, couldn't match American forces possessing immediate, responsive flame support at the company level integrated with superior tactics, training, and logistics systems. When Corporal Herschel Williams eliminated 7 Japanese pillboxes with coordinated attacks on Iwo Jima, he was applying FISA's napalm technology and American tactical innovations in ways that university researchers never could have imagined. When Marine teams systematically reduced cave complexes throughout the Pacific, they demonstrated how superior technology, combined with expert training, could overcome the most determined defensive preparations. When American assault teams eliminated thousands of fortified installations across Pacific battlefields, they proved how scientific innovation could revolutionize infantry warfare when supported by adequate industrial production, comprehensive training programs, and flexible tactical doctrine that emphasized individual initiative and small unit effectiveness. The Japanese defenders who faced American flame weapon attacks at Tarawa, Saipan, Guam, Iwo Jima, and Okinawa encountered weapons that fundamentally transformed battlefield dynamics. No defensive installation, regardless of construction quality or occupant determination, could withstand systematic incendiary attacks supported by coordinated American tactical methods. The napalm flames that eliminated Japanese defensive installations represented more than superior firepower, WPs. They demonstrated American approaches to warfare that emphasized technological innovation, industrial capacity, systematic tactical development, and comprehensive training over traditional military virtues like individual courage, defensive preparation, or acceptance of casualties. Japanese military philosophy had emphasized spiritual strength, defensive tenacity, and willingness to die in prepared positions, but these traditional military qualities proved inadequate against enemies equipped with weapons that could neutralize any defensive installation within minutes, while supported by tactical systems that maximized technological place advantages. From Pfizer's Harvard laboratory through American industrial production facilities to Pacific battlefields, the portable flame weapon connected scientific research with tactical revolution, demonstrating how university-based innovation could transform military capabilities when supported by democratic industrial capacity and flexible tactical doctrine. American company commanders who integrated these weapons into assault operations weren't just employing advanced equipment, they were implementing tactical doctrines that permanently transformed infantry combat by providing small units with capabilities that had previously required specialized support or heavy weapons systems. Japanese soldiers defending supposedly impregnable fortified installations discovered that technological superiority, supported by adequate training and flexible tactics, could overcome any defensive preparation, regardless of engineering sophistication or occupant determination. Traditional military approaches based on static defense and individual heroism became obsolete when confronted by systematic application of superior technology. When the last attack occurred on August 15, 1945, it marked not just the end of World War II, but the conclusion of an era when defensive fortification alone could determine battle outcomes. FISA's revolutionary napalm technology had given American infantry companies the capability to eliminate any defensive installation, coordinate attacks with mathematical precision, and dominate battlefields through systematic application of superior equipment and tactics. The portable flame weapons that shocked Japanese units throughout the Pacific represented the triumph of scientific innovation over traditional warfare, democratic industrial capacity over authoritarian resource allocation, and systematic tactical development over individual heroism, unsupported by adequate technology and training. In Mana-On and M22 systems projecting napalm streams up to 40 meters with devastating precision, Japanese military leaders witnessed the future of warfare and realized their empire faced enemies who had fundamentally altered the relationship between technology and tactics in modern combat. The weapons that eliminated thousands of defensive installations demonstrated how American approaches to military problems, emphasizing research, development, mass production, comprehensive training, and tactical flexibility, AIM, could create decisive advantages over enemies relying on traditional approaches regardless of their courage, determination, or defensive preparations. The legacy of American development extends beyond World War II tactical success to demonstrate how democratic societies can mobilize scientific research, industrial capacity, and military innovation to create decisive technological advantages when facing determined enemies. Herschel Williams, Louis Fieser, and thousands of other Americans proved that individual initiative supported by systematic national effort could overcome any challenge through dedication, innovation, and comprehensive application of democratic industrial capabilities. The transformation of American infantry capabilities through flame weapon development represented more than just technological advancement. It embodied the democratic approach to warfare that emphasized individual initiative, scientific innovation, and industrial capacity over traditional military hierarchies based on rigid doctrine and individual sacrifice, unsupported by adequate technology. This philosophical approach to military problems would continue influencing American tactical development long after flame weapons themselves became obsolete, establishing principles of technological superiority, flexible doctrine, and comprehensive training that would characterize American military capabilities throughout the remainder of the 20th century and beyond.